Let's talk about the charging RC circuit. An RC circuit is when you have a resistor and a capacitor connected in series. In the charging RC circuit, that means that there is a power source or battery connected to them. And that's what we have here. We have this battery connected to the resistor and the capacitor, forming a complete circuit. So this is the charging RC circuit. And in this situation, the capacitor begins uncharged. There's no charge on the capacitor at the very beginning. And so what's going to happen here is once you've turned this switch on, you connect everything, what's going to happen is electrons are going to come out the negative terminal, going to go down and be deposited on this plate of the capacitor. So of course this plate is going to become negatively charged and the other plate will become positively charged. And here I've got a graph of charge on the capacitor versus time. And since the capacitor is initially uncharged, so we start down at 0, but because it's initially uncharged, there's nothing to resist the electrons being placed on the capacitor. So electrons get placed on quite quickly. But of course, in accordance with Coulomb's law, like polarities repel each other. So the electrons, as you put more on there, they're going to repel each other. They all have the same polarity. There's going to be repulsion. So the more charges, the more electrons that get placed on the plate, on the capacitor, the more repulsion, and that's going to, that's going to make it harder to put subsequent electrons on there. And there's going to be a point where eventually the battery just can't put more charges on because the repulsion is too great. And so the charge on the capacitor is going to max out. And so we get this curve here. It's an asymptotic curve. It's asymptotically approaching what we're just going to call Q max. Okay, now let's take a look at the loop rule. Let's use the loop rule here. So I'm going to go clockwise. And if I do that, that means I start with a V naught. It's going to be minus VR. And because I'm going to cross the capacitor from positive to negative, because I'm going clockwise, so positive to negative, it's going to be minus VC. That's going to equal 0. And we'll stick in the relationships for voltage for both the resistor and the capacitor. And we get that. Okay, now let's look at some special situations. Let's look at t equals 0. So let's look at the beginning. In the beginning, we know that there's no charge on the capacitor. Q equals 0. So this term is gone in the beginning. And I just have V naught minus IR. Now, of course, this would equal 0. I'm just going to move it to the other side and say V naught equals IR, and this is the initial current. Okay. Let's look at a different situation. We'll look at when t equals infinity. So in that case, that's when Q is going to equal Q max. Now, important to remember that I is delta Q over delta t. So the slope of this graph, the slope tells me the current. Well, you can see that up here, this is flattening out. The current is going to 0. The slope is going to 0, so the current's going to 0. That means after an infinite amount of time has passed, this term goes away. This is 0. And so what I'm left with is V naught minus Q over C. Of course, that just equals 0, so I'll set them equal to each other. And the Q is really Q max. So I've got these relationships that I can get by looking at t equals 0 and t equals infinity. If you use calculus, you can go through and derive the relationship for the charge on the capacitor. It turns out to be this. Q sub c, that's the charge on the capacitor, equals Q max times the quantity of 1 minus e to the negative t over tau, where tau is called the time constant, and it's RC. And in terms of MKS units, time is measured in seconds, resistance is ohms, and capacitance is farads. So a second is equal to an ohm times a farad. Now, one thing I want to mention about this formula and all the other formulas there, the other exponential formulas we have for RC circuits. This is a model, and the model assumes that the charge can come in any size, however big or small you want it to be as the current is flowing. But in fact, the current comes in discrete packages. Specifically, it comes in electrons. It's the electrons that are actually flowing. So it can't come in any amount. An electron has a specific charge, and that's the smallest amount of charge we can have. And so consequently, this is a model. It works very, very well, but it's essentially based on charge being continuous, but it's not. It's discrete. And so it is technically incorrect, but that is only going to matter when you're dealing with very small amounts of charge. For the huge amounts of charge that we find in our everyday circuits, this model is excellent. Matches extremely well with what actually happens. Okay, so we've talked about the charge. Now, of course, we can see here, we know the voltage across capacitor is Q over C, so you can just divide this by C to get the voltage across the capacitor and get the general relationship for that. Now, if we look at the current, for the current here, we have I equals delta Q over delta T. Okay. And we see that the current starts out very high, but then it gets smaller and smaller and goes to 0. This is actually exponential decay. What's happening here is the current is decaying exponentially. And this is the relationship for that. And again, using calculus, this can be derived, but we're not going to worry about that. So if I were to plot this, the current it would start here at some value. This value would be the initial current way up here, and it decays exponentially. That's how the current behaves. Okay, so let's talk about one last remaining situation that we need to discuss, and that's when t equals tau. When t equals tau, let's start by looking at the current. That's going to be I equals I initial. If t equals tau, this is going to be e to the minus 1. Well, it turns out that e to the minus 1 is approximately 0.368. Okay. If you go through and do this here with this formula, what you get is Q sub c equals Q max 1 minus e to the negative 1. And so Q sub c it's approximately equal to 0.632 Q max. This is this very simple relationship, this idea that, of course, at some point the time is going to equal the time constant, because the time constant is just some number. I get that number by taking the resistance times the capacitance. Okay? And when the time equals the time constant, then if we're talking about the current is just under 37% of what it started at. If we're looking at the charge of the capacitor, it's just over 63% of what its max value is going to be. And so we can look at graphs. So if we come down here to our graph, if I'm talking about the current, if I say, okay, right here, let's say that's 0.368. That's a terrible 8. 3.68 of the initial current, okay? Okay, well, I go across. It's right there. And then if I go right straight down, that's got to be tau. That has got to be tau. If I'm talking about the charge, what I would be looking for is the 0.632. Okay, well, that is going to be somewhere around here. That's 0.632 of Q max. And if I go down, it's, of course, the same tau if I'm talking about the same circuit. So this is the charging RC circuit. Just a real quick summary of how it works. And if you're wondering about the discharging RC circuit, you'll want to watch the video on that.